In Unit 1, we studied manipulation of algebraic expressions. Then we progressed to solving one-variable equations in Unit 2. Now we're ready to examine two-variable equations. In Unit 3, we'll study a special type of two-variable equation called a function. Let's begin by taking some time to get to know relations and functions. First of all, a relation is any correspondence between two sets. The first set is called the domain, and the second set is called the range. A relation, that is a correspondence between two sets, in which each element x of the domain, the first set, corresponds to exactly one element y in the range, the second set, is called a function. So a function is a relation, but it satisfies a more stringent condition. That is, every element of the first set has to have a unique element from the second set paired with it. In general, x is what we call the independent variable, and y is then the dependent variable, although the variables can change with different models. Note that relations and functions can be expressed as sets of ordered pairs, tables, mappings, graphs, or equations. On example 1, our purpose will be to identify the domain and range of each relation and then determine if the relation is a function. On example A, notice we have a set of ordered pairs. Anytime you see the curly braces, that indicates a set of something, and the elements of the set will be separated by commas. So the first element of this set is an ordered pair, the second set is an ordered pair, and the same for the third. Now, each component of the ordered pair has a special role. The first component is the x value from the domain. The second element of each ordered pair is the y value from the range. Now, if you want to know a little trivia, the x component of an ordered pair is called the abscissa, and the y coordinate is called the ordinate, just in case you need to know that playing Jeopardy sometime. So from this relation, we want to describe the domain and the range. The domain is going to be the set of all first components of each ordered pair. So this consists of -4, -3, and 3. The range is going to consist of the second element of each ordered pair. So we have 0, 1, and then 1 repeats again for that third element, but we don't need to repeat it in our range. So now the question is this relation a function? This will be a function if every element from the domain has a unique partner from the range. So let's individually look at each ordered pair. The x value of my first ordered pair is -4, and it pairs up with the y value 0. Notice -4 doesn't have any other y value paired with it throughout the function. The same is going to be true for -3, which pairs with 1, and 3, which pairs with 1. Now, the different x values in those last two ordered pairs do have the same y value, but if I just look at -3, it doesn't pair up with another y value, so we say it has a unique y value. And 3 doesn't pair up with any other y value, so it also has a unique y value. For those reasons, this is a function. Now that can be a little bit confusing, so you may want to make yourself a note. In a function, the y value can repeat. Let's take a look at our next example. Again, we have a set of ordered pairs, and we want to form the domain by picking off the first component of each ordered pair. So the domain consists of elements -4, 0, 2, and then -4 repeats again. The range is going to be the second element of each ordered pair. This includes 3, 6, 8, and 5. Now we want to decipher, is this relation a function? Does each x value have a unique y value? So hopefully the first and last ordered pairs there catch your attention. Notice we have the x value -4 paired up with 3, but the same x value pairs up with a different y value in this ordered pair. So we have one x with two different y values. Therefore, this is not a function. To contrast this with the first example, notice x cannot repeat in a function. On examples A and B, the relation was presented as a set of ordered pairs. On examples C and D, the relation is presented as a mapping. In the first set, we have elements from the domain, and in the second set, we have elements from the range. The arrows from one set to the next indicate the relation. So notice from the domain, we have A pairing up with 3 from the second set, so we could write that as the ordered pair A3. We also have B pairing up with 1, so we could write that as the ordered pair B1. And finally, C corresponds to 3, so we could write that as the ordered pair C3. Now, observe there's a couple of elements from that second set that were not used. 2 is not going to be part of the range, and 4 is not going to be part of the range. So we could say our domain consists of elements A, B, and C, and the range has 2 possible values, 1 and 3. Now we need to determine if this is a function. Does every x value, or does every first component, have a unique second component? Again, what catches our eye here is this repeating 3. But notice the component A only has a unique partner 3, and C from the domain has a unique partner from the range as well. And remember, in a function, it is possible for that second component, the y, to repeat. So here is an example of a function. B, we have a similar situation where we're going to pick up domain values from the first set, and we're going to pick up range values from the second set. The relation is illustrated by the arrows. So A maps to 1, that gives us the ordered pair A1. B maps to 2, that gives us ordered pair B2. C maps also to 2, so we have ordered pair C2. And then C maps to 3 as well, so we have ordered pair C3. Notice 4 was not used from that second set. So our domain consists of elements A, B, and C, and the range this time consists of elements 1, 2, and 3. As for determining if this is a function, notice we have one x value, or one first component, with 2 different second components, or 2 different y values. As you recall, the x cannot repeat in a function, so this is not a function. You can also diagnose this directly from the mapping if you notice that you have 2 arrows coming out of C, whereas in our first example, we only had 1 arrow coming out of each element of the domain. The previous relations and functions contained a finite number of ordered pairs, but if the relation or function contains an infinite number of ordered pairs, we can represent it with a graph or equation. And so in most cases, we'll be dealing with graphs or equations. We'll begin by examining graphs. An easy way to determine if a relation is a function, if it's presented as a graph, is by using something called the vertical line test. A set of points in the xy plane is the graph of a function if and only if every vertical line intersects the graph in at most one point. Let's apply this on example 2. Use the vertical line test to determine if the following graphs are functions. Now notice we have a graph in the xy plane, and along this graph we have many ordered pairs. We could identify a couple of them. For example, that's the ordered pair 2, 1. Here's the ordered pair 0, -3. Here's the ordered pair -2 and 1. But it would take us a really long time to list the ordered pairs that belong to this relation because we have a continuous curve here. So we're looking at every possible point between the ordered pairs. Also observe that there's arrows on the end of this graph. So this smooth curve continues even beyond what we can see. So we have an infinite number of ordered pairs represented on this snapshot of a graph. We want to use the vertical line test to determine if it's a function. So we're going to construct several vertical lines, remember vertical means up and down, to see if we can intersect that graph in more than one point. And notice, no matter how I construct my vertical line, each one only intersects the graph in a single point. That means this is a function. It passes the vertical line test. But notice in the next example, I can find a vertical line that intersects the graph very easily in more than one point. Because it intersects in more than one point, we say this is not a function. It fails the vertical line test. Now, let's associate this with the definition that we presented earlier. Observe that this vertical line intersects in 2 points. I can identify the ordered pairs of those intersection points as 4, 2 and 4, negative 2. So we have one x value that has 2 different y values. Remember, the definition of a function says that every x value can only have one or a unique y value. So if I have 2 points that are directly above each other on a vertical line, they're always going to have the same x value but a different y value. So the vertical line test is the visual application of that definition. But once you know the vertical line test, it's a pretty easy thing to run. At a glance, you can tell very quickly if you're dealing with a function. Because every vertical line intersects this graph in only one point, we can see this one is the graph of a function. And for our last example, very quickly you can tell I can find a vertical line that intersects in more than one point, so this is not a function. So that's a brief introduction to functions presented in different modalities. And you'll want to be able to determine the difference between a relation and a function.